start, yeah. Today I'm going to talk to you about the frame interpolation using motion compensation for video coding. Here's the outline of today's presentation. We start from a brief introduction about what is the frame interpolation and its motivation. Then I will introduce three interpolation methods like forward estimation, half-pixel procedure method, and the bi-directional estimation. Finally, I will show some results by using different interpolation methods. Let's see what's the interpolation. In mathematics, interpolation is the method of constructing new data based on some known data points. We can see we have a few data points or sampled from some function, and it looks like a sinusoidal curves, right? And here's an example of linear interpolation, in which the adjacent points are connected together. Yeah, we can see the reconstruct curve is not very smooth by using linear interpolation method. In this slide, we show another example by using the cubic interpolation method. We can see the right circle curve looks much smoother. And of course, there are many other different data interpolation methods which can be used for different purposes, but we won't discuss those interpolation methods in today's presentation. Instead, we will focus on the frame interpolation for video coding. Here is an example of frame interpolation. It's a form of video processing.
So in the interpolation, the size, the size of input and output thing is the same?
Yeah, the same. Yeah, it's a kind of video processing method in which the intermediate frame are generated between existing ones by using the adjacent frame. And we can see in this example, the frame T and the frame T plus 2 was interpolated by using the information from their previous and afterward frame. And I see the motivation of the frame interpolation. There are mainly two motivations of frame interpolation. One is to improve the visualization quality. Another one is for video compression. For the first purpose, the frame interpolation can make the video looks more smooth. For example, the film may be captured or recorded at 24 frames per second. But right now, the current HD TV works at maybe 30, 60, or even 120 frames per second. So the additional frame will be interpolated by the TV themselves, yeah, which makes the video look more smooth, and you can get more details in a video sequence. The other purpose is for video compression. It's very intuitive. By comparison the video, we can save a lot of bandwidth, we can save the space. And one way to achieve this goal is to just drop some frames. For example, we can drop the even frames, only send the old frames, then we can interpolate those even frames by using receive the old frames. Another usage is we can use the frame interpolation to generate set information for distributed source coding. It's another technique we won't discuss it in detail today. Finally, it can be used to remove the redundancy used in the H.264, the advanced video coding technique.
What is distributed video coding?
Okay, this distributed video coding means you have two separate sensors, camera sensor, and those two sensors cannot communicate with each other.
Mm-hmm.
So, in the traditional way, if you know this sensor can communicate with each other, they can reduce the redundancy by explore the spatial or temporal redundancy. but if you cannot communicate with each other, they should compress the video independently. By using the distributed source coding framework, it can be proved that the separate encoding can achieve the same compression rate as the joint encoding. So in this way, you need a set information, and you can compress the video into single, and as a decoder, you can make a joint decoding based on the set information and the single. So in this case, you need to generate some set information according to some frame from another sensor. So this is another purpose for the frame interpolation for Bilinear surface.
What do you mean as a bandwidth space?
Bandwidth. Suppose you are doing the internet streaming, video streaming.
Oh, okay.
Right? Yeah.
The bandwidth of the internet.
Yeah.
Oh.
Yeah, at your home you only have limited bandwidth, but you
Some
want
of the
to
frames
just drop, make sure you can move the video smoothly. You don't need waiting for buffer.
Yeah.
Right? And different with the distributed source coding, our distributed video coding, the traditional video coding is centralized in a centralized fashion. The encoder have all the information. For example, you have a video, and there are a lot of redundancy between the adjacent video. Then you can try to reduce this redundancy. Then you can compress this video. So the frame interpolation can be used to remove this redundancy.
Interpolation just for two images?
You can do multiple images.
Yeah, I mean for the video.
For the
each frame, just use the previous image and.
The simplest way, you can use only one frame. I can show you later.
Oh.
You can use multiple frames.
Okay.
Yeah, you can use 2, 4, 6. Yeah, depends on your problem. Here is a key idea of video compression, such as the H.264 protocol. The encoder predicts a new frame by using the frame interpolation method from adjacent frame and only code the prediction error. Then we can save a lot of space. But those regions cannot be predicted very well. Well, we coded directly use some discrete cosine transform-based method. And the frame interpolation works on a micro block. The size of the block can be 60 pixels by 60 pixels, for example, like this. You can increase or decrease your size, which will increase the complexity. And each block can be calculated independently. So you can parallel this interpolation algorithm. Now I will show you why the frame interpolation is possible. The basic assumption of the characteristic of the typical video is that the adjacent frames are similar and the change are due to the object and the camera motion. This is the highly correlated in the time domain. It has a temporal correlation. For example, we can see in the left-hand side, the frame T-1 has a car at the left side, but in the frame T+1, the only difference is the car from the right side move to the right side, right? So we can reduce the redundancy of the moved region by using some technique. I will show you the frame interpolation can achieve this goal. Now I will show you the pixel-wise absolute difference between the two adjacent frame with and without motion combination. We can see here on the upper left-hand side is frame t minus 1 and the right side is frame t plus 1. And the absolute difference, the pixel-wise absolute difference without motion combination is showing on the lower right left-hand side. Here the darker point means a smaller difference, and the brighter means a larger difference. So we can see on the lower left-hand side there are some very obvious difference can be observed. And if we use some motion compensation technique, we can generate interpolated frame. Then we use this interpolated frame minus the previous frame. Then we can get the absolute difference is much smaller than that one without motion compensation.
Yeah, both of them, the difference between the frame T on this one and frame T.
No. This is the difference between the lower left hand is the difference between the frame T plus 1 and the T minus 1.
And that one?
That one is the interpolated frame based on the frame T plus 1 and the T minus 1. And the difference between the interpolated frame
and that one is interpolated, and after that the difference.
Yes.
Okay, this one is difference between interpolated with
And the frame T minus 1.
Minus one, the previous one?
Yeah.
And that one is just for both of them?
Yes. So we can see the interpolated frame can dramatically reduce the absolute difference. In this way, we can only code those regions that cannot be predicted very well. Then we can save a lot of bits of space of bandwidth.
Interpolating just for the finding the drop frames.
There's one purpose is to find the drop frame, and the simplest way to compress the video is drop frames. You can do better. You can compress that frame only on the region that cannot be predicted very well.
And-
You know that.
And the size, you said that the size of input and output are same, yeah?
Yes.
For example, Lanxos or Bilinear, they are interpreted, they are interpolation method, but most of them are, just apply for example, the small image, and then they can just, the result they can have the larger image.
Yeah, because it's a block-wise, so you do the motion compensation for each block. So if you have a large image, you can partition those large image into small blocks.
No. I mean that the interpolation method is just for the same size of the images as input and output.
Oh no! You can have different size. Your anchor frame and your target frame can be have different size. Different size. Yeah. It doesn't matter. I will show you the algorithm. You will see. Yeah, it doesn't depend on your size.
Yeah, for example, for super resolution, we have something like that. We're just working on the low resolution image, and after that just have the high resolution. And I think that the interpolation method just sometimes go something like that. Go on the small image.
No, there's no such constraint. It can be smaller than that or larger than. It doesn't matter. I will show you later.
Okay.
Yeah. They have example.
Okay.
Yeah.
Thank you.
Maybe I can answer your question later. Yeah. Now I will introduce the key idea of using block matching algorithm for motion estimation. First, each frame is partitioned into many non-overlapped macro blocks, as we saw in this slide. And then each macro block in the forward frame, the right-hand figure. Then for each macro block in the forward frame, we try to search a block in the backward frame on the left-hand side that has the oldest matching error. Here we can define different metrics for quantify the matching error, such as the mean square error or mean absolute distance. The basic idea is just the block matching and minimize the oldest matching error.
This block need to be on this, can be anywhere or?
Yeah, it can be anywhere. I have a detailed example in this slide. Yeah. So we said that the forward from we call the forward from frame as anchor frame and the backward as target frame. For the anchor frame here, we choose a block we want to find a matching. I cannot write on the side. We can see on the right hand side, the anchor frame has a macro block in a bold square. The current block BM subscribe M. The size of this block is 16 pixel by 16 pixel. And the corresponding block in the target frame is also shown in a bold square box, right? We can see in the same occasion, both two blocks are quite different. And given a search region, in this case, the search region can be 3 times larger than the macro block. Here is a 9 by 9 block. Yeah, maybe I can show you here. Here is the location of the anchor frame, the current block here, and the corresponding block is here. They have the same location, but we can see those two blocks are quite different. And given a search region, for example, we can say the search region is maybe 9 by 9, 6 by 6. Yeah, maybe just this region. This is a 3 by 3 big box, right? Then we can move this box all around this 3 by 3 big box. You can use the moving step can be a pixel or sub-pixel. So in this way, we can theoretically we can find a best match here. In here, we can minimize the matching error, such as the mean square error or the mean absolute distance. So yeah, the mathematical formula is given here. We try to minimize some cost function, given some motion vector.
Is dx the square of the forward anchor frame?
dx is the displacement. Yeah, it's the displacement of this current block. In this way, it may be minus 1 point something.
XF.
You may see that?
No, XF.
XF? Oh yeah. XF is the forward frame. XF is the forward frame. X and Y are the location of the pixel. Here, XY is belong to this current block. here X size are all the pixels belongs to this current block.
And XB is
XB is the backward frame here.
That's the distance between two blocks. And this MAD.
Yeah, this MAD means the mean absolute distance. So this is the pixel-wise distance. Here XD and dx and dy are the horizontal and vertical displacement. You can also replace this mean absolute distance by mean square distance. And finally, we try to minimize this cost function.
M is the size of the.
Yeah, I mean it's the size of the search region. In this case, maybe -3 and +3. It's 3 times of the block size. It's not 3 pixels. Any question about? So we call this extensive block matching algorithm. Yeah, here is the summary of the aforementioned block matching method, and we can skip it. I think I have explained those. Yeah.
MV is the motion function.
Yeah, MV is the motion vector. We call dx and dy is the motion vector.
No, MB is the motion block.
Oh no, MB is a macro block.
Oh,
Yeah, it's this bold implied block. And here is the example. We can see the two frame, the backward frame and the forward frame, and we can calculate the motion vector, follow the block matching algorithm. Then we can replace the current macro block by the block was found in the block matching algorithm. We just simply replace those blocks, and we can get a new predict frame for frame t plus 1. So in the lower left-hand side figure, we saw the motion vector, and the lower right-hand side is the predict frame. You can see there are a lot of squares in the lower right-hand side because we just simply replace the current macro block by the block was found by using the block matching algorithm.
This predicted frame is instead of frame t+1 or
Yes.
after that. You use the motion vector between frame t-1 and t+1 and predict, for example, t+2.
No.
It's instead of the t+1 based on the motion vector. Only
Yes.
move the blocks based on the.
Yes. If the quality of the protect frame t plus 1 is good enough, then we can simply drop the frame t plus 1, right? Then we achieve the goal to compress the video. Yeah, here is the absolute difference we have showed you in the previous slides. They are the same. I see the complexity of the integral pixel exhaustive block matching algorithm. The basic assumption is that the image size is m by m, and the block size is n by n. It's n pixel by n pixel. And the search region is the minus r pixel by plus r pixel in the horizontal and the vertical region. and the search step is 1 pixel. Each time we move the searching block 1 pixel. And as defined the operation count, we suppose the minus, plus, and multiplication as a one operation. Then each candidate point, the number of candidate position in each macro block is n square, right? We should at least make n square subtraction because it's a pixel-wise absolute difference. And each block will go through all the candidates in the search region. So we have 2r plus 1 square candidate region to be searched. And for each region, we have a n square candidate position. And for the entire frame, we have m over n square macro blocks. So finally, we can calculate the complexity is m square times 2r plus 1 square. So it's independent of your block size.
For exhaustive language, how can I find R as a...
Oh, R is defined by user. The larger, it's not the larger the better. It means that if you have a large R, you have a higher possibility to find a good match maybe. Because your search region is larger. Yeah, I will show you an algorithm to improve the search region by adding some penalty. Yeah. The following is a numerical example. Suppose M is 5, 12, and 13 are 16 and 3 and 30 frames per second. We can see we need 8 times 10 to 9 operation per second. So it's very computational demanding for this algorithm. So this is why the video encoder usually very slow on the computer. And there are some improvement for the EBMA. It's called factorational accuracy. The real motion vector may not always be a multiple of pixel. So we try to allow the subpixel motion vector. Then the search step size can be less than 1 pixel. It can be half pixel or quarter pixel by using some upsampling method. So to achieve the fractional accuracy EBMA, we try to upsample the frame. First, here is the algorithm for the upsampling. It's called Bilinear Interpolation. The idea is very simple. For example, we want to make the image 2 times larger, both in the horizontal and the vertical. We just we keep the even point and change, and we interpolate some odd point between the even point, vertically and horizontally.
You want to show that how we can use the bilinear upper scaling method as a bilinear for the interpolation? Because you said that the bilinear is upper scaling, okay? For upper scaling.
Yeah, it's just for upsampling.
Yeah, it's upsample.
Yeah.
Okay. And you want to just show that how we can use the bilinear upsampling method for the interpolation?
You mean what's the purpose of this slide?
Oh yeah.
Okay. Yeah. Our purpose is frame interpolation, but if you want to make a half pixel wise the motion vector search, you should upsample your image. so that you can move your search motion vector in half pixel accuracy. So this is the pre-processing before the frame interpolation. Because traditionally you can use integer pixel step size, right? If you want to use half pixel step size, you should interpolate your original image from n by n to 2n by 2n. Then you can use the half pixel size step size. You can even use quarter step size.
So after matching, you can downsample the image back to the original.
You don't need a downsample. You just just replace your original microblock by this upsampled microblock. We just the algorithm is find a motion vector and replace the current microblock by using the microblock found in the algorithm. Yeah, this idea is very simple. We just take an average of the adjacent pixels. Then we can upsampling the image from a small size to a larger size. And then we can use the same algorithm to search the motion in the half pixel procedure.
This is on the fly. So when you execute the algorithm, you can just bilinear interpolate the image and search found region, and then you can use original.
Yes, but you can actually this is a pre-processing. You can upsampling your image before the motion estimation because it's a one-time processing. It's just upsampling your image, then you use the same algorithm. In this case, you move integer pixel step size in the upsampling image, but if you think it's compare with the original, it's a half pixel procedure. Another improvement is search region adaption. I have shown you the standard mean absolute distance like this, and we can add some penalty terms in our equation, which means if the distance becomes larger and larger, then if the motion vector becomes farther than the original point, then the distance becomes larger. We just add some penalty terms, and there's a constant k to control that, to control the weight of the penalty term. In this case, we can use a very large search region, but we can make sure the findings is not far away from the original point.
In the penalty term, the dx and dy is for the current block or from the neighbors. For example, if the neighbors has a small movement, you want to control this base. For example, if you have some neighbors that it has a small movement, and in the center we have a big movement, you want to remove this one, or you want to keep the movement of each block small.
It's depend on the multiplication of the distance.
Okay, here it's for keeping the distance close to the original
Yes,
one.
but maybe the MAD smaller, even smaller if they are very far from the original point. It depends on which part is smaller than which part. So there's a trade-off between the distance and the mean absolute distance. So there should be some balance point.
What was the K?
K is a constant to control the width of the penalty term. If K is very large, then your motion vector cannot move very far. If K is infinity, then you cannot move your motion vector away from the original point.
And you just add 1 because maybe the x will be by both of them. Would be 0.
Yeah.
But yes. But if the x and dy, both of them are equal to 0, I think MAD,
It's also 0.
yeah. Okay, because why you add 1?
K can be 0 in this case.
No, I know, but why you just add 1 to the penalty?
Oh yeah, in this case you can set K equal to 0, right? If you set K equal to 0, then it's reduced to the traditional definition of the MAD, right? And another improvement is for the reduced complexity. It's called coarse to fine estimation. We can estimate the motion vector from a lower resolution image and then gradually increase the image size. And then we can reduce the search region of the, because we have analyzed the complexity here. The complexity is depends on the M and the R. So if we use a smaller image size, they have a smaller M, right? And if we increase the resolution of the image, the corresponding region in the lower resolution can cover a certain region of the high resolution image. Then we can reduce the image size. And another improvement is frame interpolation based on multiple frame. In the previous case, we suppose we only use one frame. We use frame t minus 1 to interpolate frame t plus 1, right? We can try to use the frame t minus 1 and frame t plus 1 to interpolate frame t. In this case, we can use 2 frames. And you can also use more than 2 frames according to the similar idea. For example, if we want to use 2 frames, the basic idea just divide the motion vector by 2 and take average. We can see in the lower side, for the single frame interpolation, the interpolate frame f t plus 1 is equal to the frame f t minus 1 plus some motion vector. Just replace the corresponding vector block by the block found in the frame t minus 1. So for the multiple frame, the idea is quite simple. We divide the motion vector by 2. Then for the frame t minus 1, the direction are the same, just x plus 1 over 2 dx. The only difference is for the forward frame t plus 1, because the motion vector in the previous case is from t minus 1 to t plus 1. In this case, it's from t plus 1 to t. So we add a minus sign here. So the idea is very simple. So if you have 4 frames, you can divide by 1 over 4. You can times 1 over 4 and adjust your sign, maybe plus or minus. And
Excuse me, if you have more than 2 frames, how you can calculate the motion vector?
oh, So suppose you have a frame t minus 3 and t plus 3, right? Then you can calculate the motion vector for minus 3 and plus 3, then you get another.
This example for the foreman
Yes.
example, yeah, the camera is fixed. And
Yes.
Just, yeah, it's working there.
Yeah, but the people
Yeah.
is moving.
And if the scene was fixed,
Uh-huh.
but the camera was just moving,
Yeah.
we can use this stuff, this formula for the interpolation of that image or not.
Yes, you can, yeah.
And the result would be,
It depends on
I mean
your
that this
context.
algorithm just depend on the fixed camera or no?
No, they can be used.
You have,
I have mentioned that the basic assumption is the change are due to the object of the camera motion. So it can be the motion caused by the object of the camera. You can use the same algorithm. Yeah. Another problem about this bi-directional motion estimation is that maybe you will have more than one motion vector go through a certain interpolated frame. Yeah. I can show you an example. Oh yeah, it's here. Yeah. Yeah. For example, this is the frame t minus 1. This is the frame t plus 1. There are some macro block here, and this block match to this block, and this block match to this block. So you have two motion vector, right? And if you want to interpolate this frame t, and for this given macro block, you may have two motion vector go through this macro block. So you need to make a decision which vector it should be used for generate the interpolated frame in bi-direction. So the basic idea is try to find a vector that closest to the center of the macro block. So in this case, this motion vector is closer than this vector. So we think this vector is a good vector. So this is one problem for the bi-directional motion vector estimation. It's called a motion vector selection. Another improvement is we can refine this estimation by using selected motion vector. The algorithm are the same as the forward motion estimation. The only difference is the searching in this case is symmetric and simultaneously on the frame t minus 1 and t plus 1 to make sure the vector is still here. For example, this is the macro block at frame t we want to interpolate. And here is the search region in frame t minus 1 and t plus 1. And suppose we already got a motion vector here. Then we can use the center of the interpolated frame as the origin and move this vector symmetrically. So it can be here, here. So in this case, we can have multiple macro blocks, right? Then we can minimize the cost function again. In this case, we have 3 pairs. One of them maybe have smallest cost function. So we think this, for example, this is A1, A2, A3, and this is B. This is from here, so this is B3, and this from B2 and B1. Suppose the pair A1 and B1 can minimize the cost function. So we think this motion vector is better than other 2 motion vectors. So we choose this motion vector as the motion vector of this.
So in this case, you know the frame is what, right? I mean the T frame, you know what is it exactly, right? In this case.
No, you don't know.
Then how can you compute the cost?
Oh, the cost is the cost between A1 and B1. You don't need to know the frame T.
Oh, okay, like the cost, like, oh, okay.
So this is, in this way, we can refine the original motion vector bi-directionally. So this is another improvement for the.
But then, like, these are not compatible, right? The first approach you said, like, just try to, like, hit the central. Right?
Yes.
Okay.
Yeah. So this can improve the result.
Okay.
I will show you the result. So here's the result for a high motion sequence. Here we have a frame B, means a backward frame. The frame ID is 39, and we have a forward frame named current frame. Forward frame named frame F. Its frame ID is 41, and the current frame, the frame T, is frame 40. And we try to interpolate the frame 40. And on the lower left-hand side, we saw the image quality by using the H.264 video compression method codecs. We can see the PSNR is about 39 something. And if we only use the forward motion estimation, we got interpolated frame with PSNR about 26, and we can see a lot of artificial blocks inside the interpolated frame. If we use a bi-directional interpolation, the quality of the interpolated frame is improved from 26 to 29.
What was that?
This is the image quality generated by the H.264 codec. It's a kind of video compression codec. They're like a MPG.
And you mean that it was for, you just compare these two with this one?
Yeah,
Or
actually
the-
this one is a benchmark, right?
Oh.
The upper middle one is the original frame without any compression.
And which method did you use for this one?
It's like a benchmark. It will show you the PSNR of the other video compression technique. And the left lower right side shows if you drop some frames and only use the frame interpolation, you will get some result like this. Actually, the H.264 is based on those interpolated frame. They try to interpolate the frame first, and they will calculate the PSNR of each macro block. If the PSNR of a given macro block is larger than a threshold, they will drop that box, and at the decoder they just use interpolation. And for those box, it cannot be interpolated very well. They will encode that using some DCT-based method. So in this way, you can save a lot of space and bandwidth. This is a high motion result. You can see the backward and forward frame has a big difference. Here's a medium motion result. We can see the interpolation quality is a little better than the high motion case, right? And the last one is the low motion. In this case, we can see the visual quality is I don't want to say good enough, but it looks good. Yeah, there's no artificial box. So in this way, you can simply drop those frames. And we can see the bi-directional motion estimation always outperforms the forward motion estimation. And that's all.
I have a question. For the motion estimation, for the block of the motion that you're just find the motion that you said before, if the block, if we have the default block, I mean, like, for example, in the
Yeah.
or maybe in eyes.
Yes.
Yeah.
Yeah.
In the previous frame,
Oh, yeah.
the block
There's
is not.
another technique for your program.
Okay.
You can decrease your box size. Yeah. By default it's 60 by 16, right?
You can just
use
just
4 by 4.
just decrease the size of
Yes.
the block,
Yes.
and this problem will solve.
Yeah. Most likely will be solved if it can be solved. Yeah. I mean, in this case, I use 4 by 4. There's no improvement because you cannot find a corresponding block even by human.
Yeah.
How can you?
If the picture has rotation,
Yeah. We don't think about the rotation because the video compression is already very in a high complexity. Yeah. So if you incorporate the rotation, maybe take multiple hours to encode the video. Actually, those techniques are used in the current video compression technique. They use those techniques.
But I think I have rotation too. For example, the first one, frame B and frame F.
Yeah, they have rotation, but we
Yeah.
didn't think about it in
You
the
know,
algorithm.
Any probabilistic approach for this inference?